After watching this video lecture, students will be able to calculate the free energy change of a reaction under non-standard conditions, as well as relate the standard free energy of a process or a reaction to the equilibrium constant. So we're going to go ahead and discuss free energy under non-standard conditions. But before we actually talk about the non-standard conditions, let's go ahead and quickly review standard conditions. So for gases, the standard condition for a gas is that the gas has a partial pressure of 1 atm. For liquids and solids, they're going to be in their most stable form at a pressure of 1 atm. And solutions are going to have a 1 molar concentration. Okay, and so let's go ahead and let's look at water, liquid water, vaporizing into gaseous water. Okay, so we know that if we spill water on our countertop or on our floor, if we just leave it there, eventually when we get back, we're going to have a dry floor or dry countertop. Okay, so this process we know in our household or in ordinary conditions that we encounter, it's going to happen on its own or spontaneously. Now, this is completely counter to what we see here as our standard free energy change value. Okay, and as you can see here, our standard free energy change value here is positive. Okay, and we know that that is a non-spontaneous situation or process. Okay, so what our standard free energy is telling us is that this process will not be spontaneous at standard conditions. Okay, and so what we can infer is that the ordinary conditions of our countertop or our kitchen floor are not actually a situation where we are at standard conditions. Okay, and we can look at this from the perspective, obviously, of our H2O gas. Okay, so in order for this to be in standard conditions, it has to be at 1 atm. But if we really think about, any glass of water, what have you, right? pH2O, we're going to have bunches of molecules of gas vapor above the liquid H2O. Okay. However, if the pressure associated with these gaseous molecules of H2O does not equal 1 atm, we are not going to be at standard conditions. And if we're not at standard conditions, this value does not apply. Okay, so we're going to go ahead now and look at the correction to our delta G naught of reaction so that we can provide a free energy value that can apply at non-standard conditions. So basically, we have our delta G naught, which is referring to our free energy at standard conditions, and then we have what I like to look at as a correction value. Now, the correction value has components that we've seen before. R is the constant, 8.314 joules per mole Kelvin. So we got that gas constant. We have our temperature here in Kelvin. And then we have our reaction quotient, okay, which we have encountered before in equilibrium. Okay, and so what we're going to do is we're going to utilize this equation here to look at our free energy under standard conditions, equilibrium conditions, and non-standard conditions. So again, guys, the equation that we're going to be utilizing is delta G of the reaction is going to be equal to delta G naught plus RT ln Q. Okay, so this Q, remember reaction quotients, are going to be derived from our balanced equation, right? So we've seen this before in our equilibrium unit. Okay, so in this case, our Q value is going to be equal to pH2O. Okay, and we can represent it as QP if we wanted to, because in this case, we're only paying attention to the gaseous phases. And why is that? Remember, pure liquids and solids do not get included in the equilibrium expression or the reaction quotient. Okay, so in this case, because we are at standard conditions, we know that the partial pressure of the water is going to be 1 atm. Why? Because that's the definition of standard conditions for gases. Okay, and so what we're then going to do is calculate our delta G. So if we go ahead and we plug our values in, we have our delta G naught, which we obtained from here. We have our R value, our constant. We have our temperature in Kelvin. Okay, 25 degrees C is what we're working with. And then we plug in our Q value, which we've already said that the pressure of H2O is what the Q value is equal to. It's equal to 1 atm. Right, so we plug that in. Now, the natural log of 1 is going to be 0, so this entire component becomes 0, right? And so our delta G is going to be equal to 8.59 kilojoules per mole. Okay, so in this case, at standard conditions, our delta G, right, our corrected value is going to be equal to the 8.59. So under standard conditions, this process that we're talking about up above is going to be non-spontaneous. Okay, and let's go ahead and let's apply the same concept to equilibrium conditions. Okay, so at equilibrium, our partial pressure of our H2O gas is going to be at 0.0313 atm of pressure. Okay, and so because of what we know about our Q relationship, QP for this particular process is going to be equal to the 0.0313 atm. Okay, and we can subsequently plug this into the equation that we've been discussing so we can calculate our corrected delta G. So now that we've plugged all these into the equation, let's go ahead and bring out our calculators. And we get the values of 8.59 kilojoules per mole plus negative 8.59 times 10 to the third joules per mole. Okay, our Kelvin and our Kelvin cancel, and that's how we're ending up with our joules per mole here. Okay, now notice, guys, we can't do the mathematical operation here of addition because we have kilojoules per mole and joules per mole. So we need to manipulate this or adjust this and convert it to kilojoules or convert this one to joules. Just depends on how the question's asked. So basically, we just need to move our decimal over 3 times, and we will end up with, so 8.59 kilojoules per mole minus 8.59 kilojoules per mole, and that equals 0. So in this situation, at equilibrium conditions, we end up with a delta G equals to 0. So when delta G equals 0, we're at equilibrium, and we subsequently are in the conditions where the forward and the reverse reactions are still happening, but the overall concentrations don't change. And so for this last problem, we're going to go ahead and look at non-standard conditions. Okay, so remember, for a gas, that would mean anything other than 1 atm. So in this case, the pressure of the gas is going to be 5 times 10 to the negative third atm. So we're going to go ahead and do the same process we've done, plug in our values, and check our answers. So we've plugged this in, and we end up with the following values when we put them into our calculator. And as you can see, once again, we end up with joules and kilojoules, so we need to make that adjustment. So if we make that adjustment, we're going to end up with a delta G value of negative 4.5 kilojoules per mole. So under non-standard conditions, the process of this water, liquid water, going to its gaseous state is going to be spontaneous because our delta G of reaction is negative. Okay, so guys, hopefully you kind of see in this picture the difference between standard conditions and equilibrium conditions. They are not the same thing. And so basically, this equation here allows us to analyze processes outside of being in only standard conditions. Standard free energy change and our K, which is our equilibrium constant, can be related through this relationship. Okay, and we can derive this relationship by remembering, first of all, that at equilibrium, okay, Q is going to be equal to K, and that our delta G is going to equal 0. Okay, so if we take that into account, and then we look at our equation that we just discussed in our last slide set, okay, we can go ahead and supplement. Okay, so our Q and our K, we're going to end up with RT ln K because Q and K are equal. Okay, our delta G here is equal to 0, and our G naught here is still hanging out. So if we manipulate this equation by bringing our RT ln K to the other side, we end up with delta G naught being equal to negative RT ln K. Okay, so this is how we derive this equation, and we can utilize this equation in order to relate our free energy to our relative position in terms of products and reactants by analyzing K with respect to the free energy. So we're going to go ahead and kind of analyze this on the next slide. So we're going to go ahead and look at the interrelationship between our standard free energy change and our equilibrium position. Okay, so basically K can tell us the relative direction the reaction lies, and of course delta G naught can tell us the spontaneity of a process at standard conditions. Okay, so we know that if we have a system that's at equilibrium, in this situation our delta G naught is going to be equal to 0. In order for delta G to equal 0 in this particular equation, K has to be equal to 1 because the ln of K is going to always be 0 when K equals 1. Okay, so in this situation, we already know delta G equal to 0 indicates at equilibrium position. We're also familiar with K equaling 1 representing the same thing from previous lectures. Okay, now, where this becomes interesting or even more informative is when we start looking at K when it's either greater than or less than 1. So if K is greater than 1, we know in that situation that the relationship to products and reactants is going to be that products are going to predominate. Okay, so with a K bigger than 1, when we plug that into this equation, we get a positive ln of K, which leads to a negative delta G of reaction. Okay, and so when K is greater than 1, you're going to have a spontaneous shift towards your products. Okay, now, when K is less than 1, the opposite is going to be true. When you take the ln of K of a value less than 1, you get a negative ln of K value. Multiplied by this negative sign here, you end up with a positive delta G of reaction. So the positive delta G of reaction is going to indicate that the system is going to want to shift towards reactants in a spontaneous fashion. Okay, so this equation is very useful at standard conditions. It's going to allow you to interrelate your equilibrium constant K and your free energy change. So let's go ahead and apply this equation to a problem. Okay, so in the problem that we see below, they're telling us to calculate the equilibrium constant at 298 Kelvin with the data provided below. Okay, so we're doing this calculation for this process. Okay, they've been very nice and provided us with some delta G naught of formation values. Okay, and so they want to know about free energy in K, so we should automatically start to think about this equation right here. Okay, they're asking about K. We can easily get there utilizing this equation. Okay, now, so what we're going to go ahead and look at here is, first and foremost, we want to get our delta G naught value. Why? Because they're asking about K. We know our R value, we know our temperature, so K is really the only thing that we are needing to solve for. Okay, however, delta G has not been provided as a value that they've already given us here. We need to actually calculate that. Okay, so what we're going to use is we're going to use the methodology where we take our products and reactants and subtract them. Okay, so our delta G naught for this process is going to equal our products, which is going to be 2 moles of NO2 times our delta G of formation value for NO2, which is going to be 51.3 kilojoules per mole. Okay, and then we are going to subtract our reactants. Okay, and there's one equivalent of the N2O4. Right, so we're going to do 1 mole N2O4 times our 98.8 kilojoules per mole. Okay, and if we go ahead and we plug that into our calculator, we're going to end up with 2.8 kilojoules, okay, as our delta G naught value. Okay, and then we can subsequently plug this in. Okay, the equation that we have here is basically primed for our delta G naught value. Now, guys, I do want to point out delta G naught here is in kilojoules. Remember, our R constant is in joules, so we need to make a decision about what we're going to convert into. So we can either change this into joules or we can change our R into kilojoules. I'm going to just change our kilojoules for our delta G value into joules. So that's going to give us 2.8 times 10 to the third joules. Okay, so once we've done that, we're going to go ahead and plug our values in. Okay, so we have our 2.8 times 10 to the third joules. It's going to be equal to minus 8.314 joules per mole Kelvin times our temperature, which is going to be 298 Kelvin, okay, times our ln of K. Okay, if we go ahead and we manipulate all of this, basically we're going to end up with our ln of K being equal to minus 1.13. Okay, and if we take the natural log of both sides, we're going to have K equals e to the negative 1.13. Okay, and then if we solve this in our calculator, K is going to equal 0.32. Okay, so guys, notice we have a K that is going to be relatively small, so it's smaller than 1. So in that situation, we know that our reactants are going to be what's going to be predominating, and that's something that we can infer based on our delta G naught being positive value. That means that this forward process is not going to be spontaneous, but instead the reverse process will be spontaneous.